All right, hello there. Today we're going to do section 4.6, which is on rank and sizes of different sets of things. So it should be pretty easy. Get through it pretty quickly. All right, so this first little bit right here, it says the set of all linear combinations of the row vectors of a matrix is called the row space, just like before we had column space, now we have row space, and you write it by saying row A. All right, and so for example, if you have a matrix like that matrix there, row 1, 2, and 3, that's how you would write that. And then the row space is the span of those vectors. Now, it's a subspace of R4 because it has 4 things in it, so that's something to like kind of note for later on when we do our examples. But also note that if you were going to fix this up right here, this would ref to 1, 0, negative 3, negative 6, and 0, 1, 0, 0, and 0, 0, 0, 0. So just like with column space, you don't need duplicate rows. So only these 2 pieces would actually be in the row space. So actually, you don't really need this right here to define the row space. But anyway, all right. So the next little bit, columns of the transpose and then the rows of the original. That's just a quick little rule, so you can read through that. So this next little bit right here, when we use row operations to reduce a matrix A to matrix B, we're taking linear combinations of the rows to come up with the matrix. All right, so we could reverse this process and from B to get back to A. So basically what this is telling you is that the row space of A equals the row space of B. So if 2 matrices are row equivalent, like just mentioned above, then the row spaces are the same. If B is in echelon form, the non-zero rows of B form a basis for the row space. And so I guess what I was talking about in this example above was the basis for the row space. And so I guess you can define the row space as all 3, but then the basis for the row space, you only need the 2 right here. All right. So let's get to this example here. So you have these 2 matrices, A and B, they're row equivalent. So that means that what has happened here, you've reduced A to get to B. It's not quite in reduced row echelon form because of negatives, but that doesn't really matter. So you can still see the pivots though. All right, so this guy right here is a pivot, that guy is a pivot. Find the basis for the row space and the column space and the null space. So the row space and the column space are really simple because all I do is go back and call up the rows and columns of pivots. So the row space, so basis for the row space is the 2 rows with the pivots, but I go back to the originals. So I say negative 1, 2, 3, and 6. And the second row, 2, negative 5, negative 6, and negative 12. All right, oops, that's the wrong kind of bracket. All right, and then you have your basis for the column space is the 2 columns with the pivots. So that would be negative 1, 2, 1, and 2, negative 5, negative 3. Okay, and so you would say the dimensions are 2 for both of those things. So the dimension equals 2, and over here the dimension is 2 because there's 2 things in them. All right, and then the null space. So the null space is a little bit harder, but still we basically take it from this piece right here. So if I solve that for like x1, so remember what would happen, this would turn to a plus, and then these will all turn negative right here. This would turn to a plus, and then there's a 0 over there anyway, because null space, remember, is when you have zeros over there. So let me just write this with x1, x2, x3, and finally x4 so we can see the answers right there. All right, so actually, let's see. So it turns out x4 is one of my free variables, so that's x4. x3 is also a free variable. x2 is equal to 0, so that one's kind of easy. And then x1 would be positive 2x2 plus 3x3, and then I have plus 6x4. Right? All right, so if I look at my null space, it has x2, x3, and x4 in it. So it has 3 vectors in it. All right, x2, x3, and x4. And actually it doesn't have x2 because x2 is 0, so really it just has x3 and x4. It has 2 vectors in it. So my null space is this. It has the vector for x3 in it, which is 3, 0, 1, 0. And it has the vector for x4 in it, which is 6, 0, 0, 1. And I am getting that. Here's my 3, 0, 1, nothing over here. Here's my 6, 0, nothing again, and then 1 for the x4. All right, and the dimensions of that is 2. All right, so the rest of this is just some little things to recognize or to know. So remember, your column space and your null and your row space both have to do with the pivots, pivot rows and pivot columns. So the dimensions of the column space and the dimension of the row space are the same because they have to deal with the number of pivots. All right, and the null space, that's basically your number of free variables or your number of non-pivot columns, remember. So just like back in the other example, I had dimension 2 for my null space, so I also had 2 free variables, if you remember. All right, so here's another little rule kind of to go by. The rank is what the dimension of the column space is. Remember, the column space is equal to the row space, so the rank isn't just a new word for you. The rank is basically the number of pivot columns in a matrix, okay? And so then the number of pivot columns plus the number of non-pivot columns, which is your null space, equals the total number of columns. So that's what this little formula down here is kind of letting you know. All right, so we're going to use that in some of our problems. So if you want to basically summarize it, your rank is either of these two things. It's the dimensions of your column space, or it's the dimension, which is the same as the dimension of the row space. And these two basically are the number of pivot columns, or pivot spots. All right, that's your rank. Then you have your dimension of the null space, which is the number of free variables. Remember, free variables means non-pivot. So these two things are your rank, or either one of them. And then basically, if you take either of those and add it to your dimensions of your null space, then you get the total number of columns. Okay. All right. So that little rule to remember. So now we're going to do some examples right here. And basically, that's what this is saying right here, what we just talked about. All right, example 2. Suppose you have a 5 by 8 matrix. It has rank 5. So remember, rank is going to be the dimensions of your column space or your row space. So we have the dimension of the column space or the dimensions of the row space equals 5. All right, so that means 5 columns have a pivot. And so, yeah, all right. So that means that, so I have 8 columns, 5 of them have a pivot and 3 of them don't. So that means the dimensions of my null space are 3. All right, the dimension of my row space we already talked about is 5. And remember, rank of AT, so this guy right here, the rank of AT matches the rank of A, so that is also 5. And is column A part of 5? So are the columns, do they have 5 things in them? So yes, there are 8 columns and they have 5 things in them. So I would answer yes to that. Okay. All right. So the next one, for a 9 by 12 matrix, find the smallest possible value of the dimensions of the null space. So 9 by 12, let's see. So let's see, we could have, remember the dimensions of the null space is the free variables. So so basically 9 rows and 12 columns. So I have 9 going here and I have 12 going there. So basically at most I could have 9 in my column space or my row space. All right. So that means that I would have 3 in my null space, possibly three free variables. So that would be the least I could have, and then there could always be more. All right. So basically, I would know that the number of free variables is always going to be greater than or equal to 3. So the smallest possible value of my null space is 3. All right, this guy right here. A scientist solves a homogeneous system of 50 equations in 54 variables. So we got 50 equations and we got 54 variables. It's solvable. Finds exactly 4 of the unknowns are free variables. So basically what you have right here, 4 of these right here, there's 4 free variables. All right. So that means I have 50 left. I have a 50 by 50. So that means I have 50 pivots. Right? So that means my column space, my row space is 50, 4 free variables, and so basically everything left has an answer. So can we be certain that any associated non-homogeneous system with the same coefficients has a solution? Yeah, because basically all these pivots mean that I'm going to have a solution. I have 4 free variables that can be anything they want to be, and I don't have any rows left that can cause me a problem. So my answer to this would be yes. Okay. All right. Because the column space is less than or equal to 50, so that would be true. All right. So this last little bit right here, this should go pretty quick. I've drawn some little, I like to kind of like this one right here. I try to imagine the size right there that they're talking about. It's a little helpful sometimes. So I just find that helpful. You don't have to draw these. You can just kind of watch what's going on right here. And also up top here, we have some a continuation of your invertible matrix theorem. So there's just some rules that the next few rules that go along with your invertible matrix theorem. And there's even more later on. All right, so example 5, a 6 by 3 matrix has rank 3. So remember, rank also defines your column space and your row space. All right, so rank 3 means the dimension of your row space is also 3, and it also matches your rank of AT. So that's also 3. So remember, if you have a 6 by 3 and your row space is 3, so that means that you have 3 pivots. So that means that then you have a pivot here, and a pivot there. So that means there's no more space for a free variable. So that means that your dimensions of your null space has to be 0. All right, next one, example 6. Suppose a 5 by 6 matrix has 4 pivot columns. So I have this green one over here. It's a 5 by 6 matrix and 4 pivot columns. So let's see, 1, 2, 3, 4. Oops, whoopsie. 1, 2, 3, 4. So that means that I have room for 2 free variables at most. All right. So what is the dimension of the null space? So I could say, whoopsie, sorry about that. So my dimension of my null space would be 2. And is column space in R4? The answer to that would be no. Because if you look at my columns, they all have 5 things in them. Okay. So no, because each column has 5 entries. Okay. All right, example 7. The null space of a 7 by 6 matrix is 5-dimensional. So the null space is 5-dimensional. So it means there's 5 free variables. So that means if I have 6 columns, 5 of them are free, that means that one of them is left to be a pivot. So what is the dimension of the column space? I would have to say 1. Example 8, if the null space is 4-dimensional, 5 by 6. So that means that I have 2 columns out of these 6 left to be pivots. So what's the dimension of the row space? 2, because it matches the column space, and that was 2. All right, example 9. If you have a 4 by 3 matrix, what is the largest possible dimensions of the row space? So let's see. The row space is the number of pivots, so 4 by 3, the most pivots that I could have would be 3. So my answer to this question, the largest possible would be 3. Has to be less than or equal to 3. All right, and the last one, if A is a 6 by 4 matrix, what is the smallest possible dimension of the null space? So the least amount of null space, so the least number of free variables. So that means I want to see what the biggest amount of pivots I could have. So I could have pivot, 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 pivot. So basically, all 4 columns could be taken up by pivots, and my null space could be 0. So my answer to this, the smallest possible thing, would be 0. All right, and that's it. And I hope everything was fine with this and your homework goes well. Let me take a second. The homework for section 4.6, I will check on that and I will post that on the website because I forgot to look and see if I want to reduce it a little bit, so I will post it there. I'll talk to you later. Bye-bye.